Okay, thanks the organizer for giving me this opportunity to present our work, and also I thank the chair for the introduction. So this work is on this new chiral metal phase in quantum Hall fluid, compressible quantum Hall fluid. This work is done at Shah Institute of Nuclear Physics, is a constituent institute of HBNI and funded by DA. So, there are several speakers introduce quantum Hall effect. Basically non-interacting electrons give integer quantum Hall effect, and kinetic energy is quantized under high magnetic field. This gives this integer quantum Hall effect, and in the fractional quantum Hall effect, basically interacting electrons gives fractional quantum Hall effect, and it appears at this Jane sequence with the picture of composite fermion. This is the thing about quantum Hall effect. So, now I introduce, we want to work at compressible regime. So, we introduce what is compressible and what is incompressible. So, basically under high magnetic field there is a Landau level or lambda level. So, basically when the Fermi energy lies in the gap between the two levels, basically here the density of state is low, and here the system is incompressible, where you see the quantum Hall plateau. This is incompressible. And when actually Landau level or lambda level cross the Fermi energy, where the density of state at the Fermi energy is high, so you see finite RXX, and there is a plateau to plateau transition. We call it compressible fluid. Okay. So, basically our focus is the compressible fluid. So, basically people used to thought that there is this is a dissipative, because there are states at the Fermi surface. So, there could be diffusion or percolation. There are many kind of pictures. So, we want to explore experimentally what is the transport mechanism is that. So, we know that quantum Hall is the first topological insulator where bulk gap is created by magnetic field, and conducting surface states, here the chiral edge states. So, our motivation of this work to prove that there is a topological conductor which is gapless 2D system we can found in the compressible system. Okay, it is not the topological insulator, it is topological conductor. So, I experimentally prove what is that. So, first I will introduce our surprise, the observation of some rule of conductance. So, basically if we stay in some compressible region, so there are edge states, chiral edge states, and there are bulk states. So if we put a source, then whatever injected current that will go through the chiral edge states, and then there will be current partitioning in the bulk state as well. So, current will reach each and every contact, and this the current measured. So, when you measure current, these contacts are virtually grounded. Okay. So, this current divided by voltage is my conductance, and if we sum over this conductance, it is just the Hall conductance. So, this is the how we measure it. So, this is the topologically equivalent diagram. Okay. So, this is the same source, and there are 1, 2, 3 contacts, and we measure current and measure G1, G2, G3 from this contact, and you see there are contacts. So, we can measure. So, basically I1 plus I2 is the transmitted current. This current divided by the Hall voltage is my Hall conductance. So, basically whatever we can measure directly from the experiment, and from the sum G1, G2 plus G3 we can measure the G sum, and then we can compare. So, this is the plot. This G3, which is the blue line, you see. So, whenever there are quantum Hall plateau, this is 0.6, 0.66, this is 1, this is 2, this is 3, this is 4. So, there G3 is 0 at the quantum Hall plateau, but whenever there is a plateau to plateau transition, this G3 become finite. So, now this green curve is G1 plus G2. So, you see this is the green curve, it is quite arbitrary, looks like quite arbitrary. Now, if we add these two and take a G sum, which is the red line that we have plotted, and the GH we measure from experimentally, then you see they overlap each other. It is a magic. So, why? What is telling? So, now the thing is that I have drawn the orbits like this, but if there is a disorder, if there are percolation, scattering, there will be zigzag paths, and in that case this G sum will never reach to GH value. Okay. So, this experiment tells that there is a suppression of dissipation here. So, there is no scattering in the bulk state. So, how we prove that? This indicates, but it does not prove. So, how we prove that? So, if there is a diffusion, so we have this equivalent resistive circuit. Okay, from source to 1 there are resistance, this R1, R2 and R3, this is passing current, and there are resistance connecting these 2 and 3, 1 and 2. Since those are grounded, no current is going. And if there are percolation picture, basically it is every contact is connected this percolating channel. So, now we plot, we measure G1, G2, G3 simultaneously. So, G3 is plotted here, and G1 plus G2, which is GT, which is the green curve. Now, what we did, we do not measure G3. So, it is earlier it was grounded, now it is not grounded. Now, you see we have a open a path to go additional current. So, here G3 is finite. So, that means some current is reaching here. So, this current I am trying to push through R32 to contact 2. Then this is the this GT3 float, this is the yellow dotted line. Now, you see this exactly overlap on top each other with RMSP 0.5%. So, what does it mean? So, that means here the current is coming, but from 3 to 2 current is not going. So, this tells that there is a handedness of transport. So, because of high magnetic field, you see 2 to 13 Tesla, it is a huge range. So, basically chirality is the clockwise direction. Here basically from 3 to 2 we are trying to push in the opposite chirality direction, which is not allowed, and system is not going, in the system is not passing. So, handedness is proved. Now, how much is the handedness? So, we did another experiment. We measure the G3 conductance. Earlier used to be like this. Now, I open 1 and 2 in floating condition, then all the current in the chirality direction reaches to G3, my G3 become this orange line. So, now see this G3 1 to float recovers the Hall conductance with RMSP 0.65%. So, that means the bulk extended state is chiral and it reaches about 100% chirality. So, now if it is chiral, if there is a handedness transport, no dissipation, then what will be the conduction law? Conduction law should be universal. In our case, already we have seen this is a sum rule of conductance. Okay. So, this we have explained here, and we know, so in the system this percolation picture is not there, and basically opposite to chirality there is no quasi-particle transfer. So, basically we know for 1D dissipationless transport, this conductance is G n2 square by h. N is the number of conducting channel in 1D, but in 2D basically in the compressible fluid, this G sum is equal to GH. This is the sum rule of conductance that we want to see, and we see it should be universal. So, how you do that? So, we have shown this result that is a contact configuration independent, and as long as you measure the total whatever the current we are injecting from the source and you capture all of them between 1, 2 and 3, then you will get the sum rule. And if you float 1 and 2, we collect all the current at I3, it recovers again the Hall conductance. Then it's a geometry and length scale. So, basically in this our device, here the travel distance is 200 micrometer. If we reverse the magnetic field, my chirality is opposite. So, source to is a 20 micrometer. And again we do the same experiment, we see that G sum actually approaches GH. So, it's length scale independent. Now, we inject the carrier in the same sample, its density, its mobility is changed. Again you see that G sum follows GH. And if we increase the temperature, again you see this G sum following GH. And it is interaction independent. So, I plot between magnetic field 4 to 6 Tesla in details in here. You see there are dips in the G3, and these are 8 by 3, 5 by 2, 7 by 2, those kind of quasi-particle composite fermion states. And in that sense you see this G3 is very ugly and GT also very ugly, but if you sum them, this G sum follows GH. So, if there is a quasi-particle transport event, it follows the sum rule. Okay. So, all those results we have actually summarized in this curve, and we so basically this nu we have calculated from GH, and we see that now basically integer plateaus, it used to be wide, now it is a single point 1, 2, 3 like this. And we see that basically rest of the region is like compressible fluid, and we see always G sum is trying to follow in whatever condition we vary, the G sum is invariant. So, that is why we are saying that sum rule is the fundamental conduction law of compressible fluid, and this compressible fluid is a chiral metal. Why? Because it has a handed net transport with suppressed dissipation. Now, the physics. Why? What is the physics behind it? It is classical or quantum mechanical. So, this is the Thomas Fermi screening for 2-dimensional electron gas, this gas all gas system. This is the screening length, A is the well width, and dN d mu is the density of states. Okay. And this has been calculated by Ando in these papers. So, now from this expression we get this Ls by Lb, this ratio, and we consider this Landau level broadening, which is 1 MeV, and well with 50 nanometer. If we put all the values, we get Ls by Lb is 0.13, is much smaller than 1. So, what does it mean? That since it is a short range screening, so basically in the system there is disorder. We see there is a wide quantum Hall plateau, so that means there is a disorder, Fermi energy is pinned in the disorder in the quantum Hall plateaus. But when we are in the short range screening range in the compressible fluid, the disorder is like point disorder, okay, and rest of the thing is flat. So, it is a flat potential landscape. So, in this thing basically if there is a broken time reversal symmetry, then electron moves without any scattering. It goes from 1 to 2 following these orbits, and this is the reason this is a chiral metal, and the goblet is a 2D topological conductor. Okay. So, I want to go deep into the this problem. So, basically, so there are actually orbits, right? psi 1, this is psi 1, this is psi r2 k2, this is psi r3 kt. Let's consider this orbit. Okay, this is defined by r2 k2. K2 is the wave vector and r2 is the orbit. So if we have gas. So if we look into the wave functions, so this wave vector is propagating, and in the lateral direction it is basically shifted harmonic oscillator, and its orbit is defined by this r2. Okay, so this is moving in this direction. So here this r2 and k2, they are basically locked. So that we have solved in the quantum mechanics problem. So if you want to change this k2, immediately r2 is changed. So then basically if there are some scatterer here, so basically it hits and it has to come back to minus k2 states. So minus k2 states means it's at the same position, these states is not available. It will be different position, and if you try to take a overlap integral, this overlap integral is absolutely 0. So that means this k2 to minus k2, this kind of changeover is not possible by scattering. So that's why this basically whatever the orbits which are connecting source to the contacts, they just move forward, it cannot come back. So that's why it is chiral metal, is a gap-less 2D topological conductor. So now why we are calling it it is a phase? Because in the incompressible quantum Hall regime there is a low density of state, the screening length is very high. Okay, so Ls greater than Lb, and this G sum basically is a quantum Hall conductance, which is okay. And at the interface of incompressible and compressible region, there could be the crossover. Ls greater than Lb, there is a percolative regime like this. And within the compressible region, this Ls less than Lb, we have this chiral metal phase, and this thing actually we can see here. Look, at 2, this point, it matches exactly with this thing, and whenever we go out of 2 in the both side, we have to cross this percolative regime, and we see there is a deviation. Again it enters into the chiral metal phase in the both side. Now as we increase the temperature, this chiral path actually melts and it go into the chiral metal phase, and here RMSP is much better. As we see in the other sample, other high density sample, also it matches at high temperature. Sorry. Now I say that chiral metal phase it is dissipationless. Now the thing is that why this longitudinal resistance is finite. So this is a typical some example of quantum Hall circuits. We put the gate across the channel, and we put the filling fraction nu is equal to 2. Basically we play with one mode actually is transmitting directly and other one is rotating, and we put whatever current and we excite with the voltage and see how with Landau-Buttiger formalism we calculate what is the voltages here. So in the bulk there is no dissipation, only happen because of electrochemical potential equilibration at the contact. We see these are the list of voltages. From that we can easily calculate what is the longitudinal voltage, what is the Hall voltage, everything. So this way basically when we go into the compressible regime, we have to replace this with some compressible fluid. So this current partitioning will take place the quantum Hall A states and the bulk state, and that way we can explain in the bulk there is no dissipation, still you can have finite longitudinal resistance. So this is the how this current partitioning take place. This is explained in this paper. So now what is the significance of our discovery? So this is we have discovered this new conduction law of this chiral metal phase, which is the sum rule of conductance. Okay. Then next one is we have resolved the transport mystery. In the earlier we used to think that Rxx is finite, right? So because of dissipation or percolation, but we say no, it is originating from equilibration of electrochemical potentials. Okay. Then we have done how to verify this bulky chiral by floating contact measurement. So this is the thing. So basically our trick is that in a Hall bar you make one source, one detector, but our smartness, we have put several contacts and measure each and every contact. So it requires actually enormous. I finished. This is so basically it requires enormous facilities. Basically all the channels. Okay, you have to measure with lock-in amplifiers. So you need n numbers of lock-in or n numbers of preamplifiers. Everything. Okay. So this is one thing, and there is a boundary conditions for the chiral metal phase. So I have explained this is the hierarchy of length scales. When you have short range screening and broken time reversal symmetry by magnetic field or any means, if you do that, you will get this 2D topological conductor. Okay. And then robustness across strongly interacting system. I have shown you those data that whenever there is this composite particle or all those things, but the thing is that this chiral metal phase is the basic conduction mechanism in the system. So always it try to enforce even these chiral trajectories in strongly interacting composite quasi-particle states. So now we have introduced actually a broad paradigm of 2D correlated system. Okay, so this broken time reversal symmetry and short range screening. So we can have new paradigm of transport where you have some rule of conductance and this chiral transport. So this kind of thing can be applied to this graphene, Mori superlattice, anomalous Hall material system. So this is the regime. Actually, it's a new paradigm one has to explore in those kind of system. And now this is the future chiral electronics in semiconductor system. So what happened? People studied, invested so much time on chiral, this topological insulator. Why? To make low power chiral electronics. Okay. So in this system, what happened? At b is equal to 0, we haven't shown the data. At b is equal to 0, it is isotropic. There is a Drude transport. So as we increase the magnetic field, we actually break the time reversal symmetry and it become chiral metal phase, and we have the data that it become chiral metal, 100% chiral metal, chirality of 100% as low field as 0.3 Tesla. So that means with a permanent magnet, even we can make this semiconductor 100% chiral. And not only that, so basically the screening is not strongly temperature dependent. Okay, and also time reversal, broken time is not temperature dependent. So that's why it can, this chirality actually sustain as high temperature as 10 Kelvin. So basically this is a very nice system for future low power chiral electronics. So one can make chiral FET, chiral logic gate, chiral processor. So this is the way, and it's a semiconductor. Since it is a semiconductor, so it is easily, it is scalable, everything. Okay, so this is the significance of our work. Now I thank my collaborator. Of course, they are the students, they are the backbone of this experiment, and this Hall01 Das is a gatekeeper. Okay, so I cannot say anything without his permission. And Vladimir Umensky is the, he provided the TUDEG from Weizmann Institute, and I acknowledge all the distinct professors, and thank you for your kind attention.
Thank you very much, Dr. Bhaimakar. So, we have a time for 3-4 questions now. Yes.
Thank you for your nice work. I have a short question about this. Suppose you keep the film decreasing the magnetic field. So below the film level, many landowners are free. So how this property changes? Because chiral metal, whenever you have a magnetic field, it becomes chiral. But then when you have high magnetic field, you have this quantization issue.
Yeah. So that I have there is no data. Basically, at B is equal to 0, it is isotropic. It's a root transport. So there is a dissipation, but as we so at this thing, basically, if we see the screening length, this is still small because there is a constant density of states. Okay, so potential is a point disorder and it's a flat potential landscape, but there are scattering.
So
But
screening length and versus magnetic length is the characteristic.
yeah. So this is the thing. Whenever you actually cross that Ls by Lb less than 1, immediately you reach into the chiral metal phase. So we reach the chiral metal phase at 0.3 Tesla, just about the starting of Subnikov-Dihas oscillation.
Thank you.
Yeah. Any more question? I have a question. What's the thickness of your gallium arsenide?
This gallium arsenide quantum well, I have, sorry. This is the quantum well thickness is 50 nanometer.
So if you will vary this thickness, then
So if we decrease the thickness, then this factor will be decreased. So that's why if you work with graphene, so basically screening length will be low. So this chiral metal phase you can achieve even in 77 Kelvin. So basically it's 77K you make some kind of a chiral processor with graphene. It's a new concept.
So I see there's no more question. So let's take the speaker again.